Okay. All right, it's 3:32. I think that is a good time to start. So welcome everybody, and welcome to the Chester F. Carlson Center for Imaging Science seminar series. This is a weekly series that we have. It's been normally in person at the center itself, but of course, in lieu of the pandemic, we've been doing this online just like everybody else. And today happens to be the last day of classes for us here at RIT. And it is also the last seminar for the academic year as well. We will be picking this back up in the fall weekly. And hopefully, if you are interested in these types of seminars and we keep them going in virtual, I don't know what the status of that will be. You could see these seminars if you go to the RIT events page at the RIT website. So given that background, let me introduce today's speaker, a colleague, a friend of mine that I've known for a bunch of years now. Our paths cross in this area of hyperspectral imaging and sensing and conferences and things like this. And he's been kind enough to share some thoughts with us today as it relates to hyperspectral sensors, imaging, CAL, and a variety of things, something he knows an awful lot about. And let me just tell you 2 seconds about him in the event that you did not read his bio already. I'll keep it brief, and then we'll let Trond speak to us today. So Trond Løke, I hope I pronounced that correctly. Is that right, the last name?
Løke.
Well, I don't have, I'm close. I'm close.
You're close.
Yeah, he has a master's in photonics from Norwegian University of Science and Technology. And he calibrated and characterized NEO's first hyperspectral system in 2002. So that's a number of years ago, and was responsible for the design of HISPEC's first hyperspectral imaging system a little bit later in 2003, where he eventually became CTO. And in 2020, he became CEO of NEO that is in Oslo, Norway. So with that, normally we would welcome him, but we can virtually applause. We'll skip that and we'll let him speak to us. Take it away.
Thank you, Emmett. And thank you for having me here. Yeah, as Emmett said, I'm here to talk to you about key parameters that might ruin your hyperspectral data, or the key quality parameters in the data. And
I have to apologize and cut right into when you started. I do need to state one thing. I'm sorry, I apologize. Yeah. For those that are online, we have about 73. If you happen to be an IEEE member, I made this a geoscience remote sensing sponsored event along with our CIS program. If you happen to be an IEEE member, if you could just if you could just type in the chat window, I'm an IEEE member. I just need to make a head count for reporting. I apologize. No more interruptions.
No problems. Yeah. So I'm talking to you about some quality parameters hyperspectral imaging. I will start with a quick intro of Norsk Elektrooptikk, or in English, Norwegian Electro-Optics. Then a bit about what is hyperspectral imaging and what characterizes good hyperspectral data. Then talk about the noise sources on a detector level, and then optical quality. And I will continue talking about how we calibrate and characterize our system, and then how these parameters, or how to keep them stable. And then about 30% left of my presentation, I will go into some operational consideration for remote sensing applications from airborne and UV, and a quick comparison at the end. Yeah, NEO, we are a SME from Norway, founded in '85, a spin-off from the Norwegian Defense Research Establishment. We do research in electro-optics with objective to develop state-of-the-art products for an international market. We are today owned by a foundation, and the foundation has, they want to do research with high financial and technical risk. So we are a lot more scientists than a normal commercial company. We are, in the early days, we did project for space, for the European Space Agency and for the Norwegian oil industry. So we have commercialized quite a lot of technologies. The top 3 is laser gas spectroscopy, high specs, and underwater imaging. Today, we are about 40 employees and 20 in R&D. As I said, we are on SME, and we are collaborating a lot of EU and international R&D projects in addition to making hyperspectral systems. We have a long history of working on prestigious R&D projects with key players in the world of photonics. And at NEO, we have all the resources internally to develop, design, and produce all the electro-optical systems. I think about 5 years ago, imaging spectroscopy moved into being the main focus area of NEO. And hyperspectral imaging is the same as imaging spectroscopy, just with a high number of spectral bands. We believe that to do imaging spectroscopy, you need high quality spectrum in each pixel. So HSI's main focus has been and always will be to deliver as good spectral fidelity as possible. So with the focus on delivering sharp optics per pixel and per band, and with very low spatial and spectral distortions per pixel. Then what hyperspectral imaging is. We at NEO and HSI, we develop the push broom systems. And the hyperspectral imaging, as I said before, that is combining imaging and spectroscopy. There are many different optical architectures that can be used to make a hyperspectral system. But the end goal is always the same, is to make an image where each pixel has information from many spectral bands or many different colors. If you only have quality in mind, your highest priority should be the spectral fidelity in each pixel. Yeah, so here I start with our datasheet as a good example of a bad example. Basically, it's a datasheet. This is how all the suppliers today are presenting their cameras. And where we are presenting the spectral range, number of pixels, spatial pixels, number of bands, F number, field of view, bit resolution, noise floor, dynamic range, and so on, and the peak SNR. But actually, this datasheet doesn't tell you anything about how good your optical system is on a pixel level. It just tells you about the top level, how many spatial, how many bands. And I will dig a bit deeper into that. So what is good hyperspectral data? So traditionally, it's to have as good SNR as possible for all wavelengths. So the definition of SNR today only depends on how much light goes through the system for the different wavelengths and the detector specification. The SNR definition is definitely not enough to evaluate the quality of the data. You also need to evaluate if the whole photon hitting that detector element is from the correct place in the scene. There are a lot of other contributions that impact your data quality more than the detector noise sources. And optical distortions are usually the largest contribution to the lack of spectral fidelity in each pixel. Yeah, here you have the specification of signal to noise ratio in a hyperspectral system. The DN raw here, that's your raw data in digital numbers from your camera. Here you have photoelectrons per the DN level at saturation. So if you have a 16-bit detector, that's 65,535. So the signal here is then your raw data minus your dark current, part of your data, right? Then you have the noise contribution, which is your noise floor or the readout noise. So we usually characterize that with putting the lowest possible exposure time, no light to the system, then you can characterize the noise floor of your system. Then you have the photo noise on top of your signal and the dark current noise, because you're always subtracting a dark current, but that is usually quite much lower because you have averaged a lot of frames. I will come back to that. So on a normal silicium detector, as we see here, on the left graph, you can see the dark current for 1 millisecond exposure time. So you can see that's very low, about probably an average 1 digital number and 10 in mean DN value. While on the right side, we have illuminated the detector with very variable illumination. So you can see that the noise increases with the mean dn value with the very nice photon noise curve, which is the square root of number of electron holes pair generated on the detector element. So this is due to the fact that it's very random when the photon is hitting your detector, and this is a Poisson distributed probability function. So for silicium, you don't have any big impact from dark current as a function of exposure time. But if you move into the shortwave range, which is from 950 nanometers to 2,500 nanometers, you actually have quite a big impact from dark currents. So dark current is changing. If you see here on the top right curve, is changing quite a lot with exposure time. And basically you will have noise, photon noise on top of your dark currents, and you will have that the dark current increases linear, right, with your exposure time, eating up your dynamic range of your detector. So for sphere sensor, that needs to take into account when you calculate your S0. And of course, bad pixels for MCT and in-gas detectors, it's getting a lot better. When I started this 18 years ago, it was about 1 to 1.5% bad pixels in an MCT detector. Today, in MCT detectors, with that 20 to 30 micron pixels, you will have about 0.05% bad pixels. And then the total quantum efficiency of your hyperspectral system. So if you remember in the datasheet, usually you mention the peak SNR, but basically your camera is not just sensitive on one wavelength, so you need to know what is the total quantum efficiency for the spectral range of the camera. So then to evaluate how your zenith noise ratio is for the whole spectral range, you need to take the incoming light into consideration, the total quantum efficiency of your camera, and then you will get a zenith noise ratio curve as a function of wavelength. And then you will see that for most of the bands, you will never reach the peak SNR, right? So you will have a lot lower. And this is important to evaluate, right, for all hyperspectral systems. Yes, optics and the impact on spectral fidelity. So in a perfect hyperspectral system or hyperspectral camera, the spectrum captured by one pixel is an actual physical representation of the seen image by that specific pixel. In this case, the SNR calculation done above will be enough to evaluate the data quality. But hyperspectral cameras are never perfect, even if HSI is close. The classical zenith noise ratio definition shown above assumes that a photon hitting a detector element is supposed to be there. But if you want to evaluate the real zenith noise ratio in a scene, you need to dig deeper into the optics and the optomechanical architecture, which I will try to do now. The largest optical contribution that compromises the spectral fidelity in your data are spatial misregistration, spectral misregistration, and stray light for some architecture, not for all. So here you have some spatial misregistration parameters. So as I said in the beginning, we make push-broom systems. So if you're looking at a point source, all the energy from that point source in the ideal case should hit one column on your detector, like you see here to the left. But that is never the case. You will have the effect called keystone, which is basically that the spectral sampling, the spatial sampling is different for the different bands, which will tell that your energy from your point source will shift over to the pixel next to it. You can also have a misalignment here in the optics that causes the same effect. Then you have PSF variation, which is basically the point spread function that looks differently from different wavelengths. Then you can, of course, have the combination of the two. And then you have a blur, which is kind of not in the same optical distortions, but kind of a design choice can be in many cases, but I will discuss that later. So we wrote an article in 2020 where we looked at 70 different cameras with different amount of keystone, PSF differences, and PSF shape differences as well. And this is one of the figures from that paper. I will not go into detail here, but the conclusion is that all three parameters contribute quite a lot to the error, but the largest contribution is keystone. And I will go a bit deeper into that. This is from a different article we wrote a few years ago, in 2014 actually, in optical engineering, where we, based on our data, it was 100 gigabytes of airborne data. We added different amount of keystone, and we looked at what kind of error was introduced in that data. So we wanted to use real data to simulate this, not just made up data. So it's a bit messy graph, but on the top here, you can see the keystone from 0 to 30%. On the bottom is the pixels, and here you can see the average relative error in your spectrum. And if you can see here, if you have 30% error, keystone in your data, you have about a 7% average relative error in your data, which of course you can say that you have 1000 single noise ratio as peak in your data, but if you have 7% relative error, of course, that is not true in a real scene. It might be true into an integrating sphere, where all the intensity in each pixel is the same, but not in an actual scene. Right? So I cleaned up the graph a bit, just to show how the relative error looks with the amount of pixels, amount of keystone on the x-axis. So this has a huge impact on the spectral fidelity of the camera. The same for spectral misregistration. Basically, that is that you have different spectral sampling, different places in the field of view. So basically, your spectral vector will be different depending on where you are in the field of view. So you can of course compensate that by resampling, but you have to have a spectral matrix of the whole system and resample to the same wavelength afterwards. Then stray light. So stray light is also something that we characterize on our detectors, but there's no good standard for characterizing today. I saw that there's quite a few people here from the P4001 group, so I have one slide about that at the end. But so today there are no standard about actually characterizing this. And the way we do it both spectrally and spatially by having very narrow spectral sources and point sources, and we look at the energy a few pixels away from those, and we scan it across the whole field of view to measure the stray light. So basically, stray light is not, it's basically light that's hitting the detector, and it's not supposed to be light. It can be scattering from the optics, it can be reflections from the mechanics inside, and so on. Yeah, then sharpness. So sharpness is not a quality parameter like the previously mentioned optical distortions. Of course, as long as the sharpness is the same for all positions in the spectral vector. An optical system can be designed for a specific detector to be as sharp as possible. Or a detector can be chosen to resolute the PSF with more than one pixel, like this, for example. So, but in high space, we tend to make very sharp cameras. So sharpness, of course, will influence the errors that is introduced by misregistration. And I have 3 points here, which I want to mention in that aspect. So for any given detector that you have, with a given detector pitch, the imaging spectrometer will always output more information with sharper optics. On the other hand, sampling the PSF with more than one pixel gives you more information about the PSF. But for a given detector, it will reduce the resolution of the system. But then on the other hand, from the first point, right, for any given optical system, it will always output more information the more pixels you have per point of function. So it's important to evaluate, right, the sharpness and the number of effective bands of pixel in your hyperspectral camera, not just the top level amount of pixels and amount of bands, which you saw in the example of a datasheet in the beginning. So for sharpness, the key quality parameters for sharpness is then the effective number of pixels and the effective number of bands, and also the average spatial PSF width, which is again the number of pixels divided by the effective number of pixels. So, and also the average spectral PSF width. So when buying a camera, we think at least that price per effective pixel is a good measure or evaluation criteria. And then light sensitivity. If you remember the data sheet I said something about noise flow or readout noise. This tells you only the limitation of your detector, right? But it doesn't tell you how much light goes through the optics and how much noise is on the dark current. So the key parameters that gives you some indication about the light sensitivity is the F number, is the total quantum efficiency of your camera, the dark current as a function of exposure time, and the noise floor. But there is one parameter that, of course, tells you all this in one graph. That's the noise equivalent spectral radiance. That includes all the above-mentioned noise sources, and it's a measure of how much light is needed to give you a signal polarization of 1 for a given exposure time. A very common mistake here is for a sphere detector to not take the dark current into consideration, for example. Then traceable calibration. So a traceable calibration means that you have a NIST or PPB or other traceable radiometric calibration, an accurate spectral calibration, and an accurate geometric characterization. Spectral calibration, the goal is to characterize the center wavelength of every band of your camera. So here we illuminate an integrating sphere with many different sources. It can be a monochromator, scanning through the whole spectral range, tunable laser as well. Those are usually quite expensive, at least if you're covering your whole spectral range. You have different laser sources and spectral calibration lamps like mercury, xenon, krypton, and argon. So depending on your dispersive element used, there are many ways of calculating a spectral vector. It's quite different how the spectral sampling look if you use a prism relative to a grating, for example. And the measurements is looking into an integrated sphere, which I said, with as many sources as you feel you need as a supplier to achieve the required spectral accuracy that you are promising. And the output is a spectral vector or a matrix, depending on if you have a lot of smile or not. And of course, the accuracy of the calibration should always be an output of the calibration. And here is an example of a calibration done on one of our Mjolnir systems on the right, the UAV camera. Then the radiometric calibration. So the goal there is to generate calibration data for converting raw digital numbers into absolute radiance data. Yeah, for how we do it in HySpecs is actually based on a document that Torbjørn Skåli wrote way back in 2005, I think. 2006 is there. About how we divide up the responsivity matrix here. The top formula here shows you the raw digital number as a function of incoming photons. And we have divided here the response matrix into the quantum efficiency vector and an RE matrix. So I will come back to why we do that. And of course, we have the background here, or the dark current here and there. And then on the bottom formula, you can see the number of incoming photons as a function of radiance. And of course, here you will have the integration time as a function, the area of the aperture, solid angle, and then also your spectral calibration here on the right. So this is a formula then for the radiance, right? Where you have your digital numbers here, you have your dark current, you have your spectral calibration here, and your radiometric calibration is basically to calculate the quantum efficiency vector and the response matrix. So the reason for us to divide those things is, of course, it's nice to have a quantum efficiency vector that shows you the total quantum efficiency of your camera, which is also kind of a very good graph to show. Shows you the relative spectral response of your camera as well. But another point or reason for us doing this is that, for example, for a silicium detector, the dynamic range in the quantum efficiency vector is quite large. So if, for example, you're doing some real-time calibration, you have a limited bandwidth, and you want to keep your dynamic of your data as low as possible, dividing by the RE matrix will basically not increase the dynamic range of the data. While if you divide by the quantum efficiency, you can exceed your bit resolution of your data. Yeah, so the radiometric calibration setup is, as you see here on the right, we are looking into an integrating sphere and with a known output radiance. And yeah, for us at least, the typical source is a tungsten halogen lamp. And the output is uniform. And we know that because we have been around in Europe and US and tested many integrating spheres and testing the uniformity. Yeah, so yeah, the results here is that every pixel is illuminated, right, with the same amount of light, and then you can characterize your detector very accurately. Then geometric characterization. So for many applications, for example, airborne and UAV, you need a very accurate geometric model of the camera. I've seen some examples of suppliers on this saying that their field of view is 20 degrees and not actually characterizing the angular field of view of each pixel. So that is what the geometric model or the sensor model is, with the angle of each pixel. The normal way of doing this is to use a large collimator with a point source in the focal point of the collimator and scanning this point source across the whole field of view of your camera with a very fine resolution. So we scan across every pixel with 1/100th of a pixel step and with a 0.79 arcsecond resolution on the encoder on the stage to get a very good accurate sensor model. And the same characterization setup can also be used for characterizing spatial misregistration, for example. And here's an example of our new 640 camera, where we show here on the right the actual sensor model, where each pixel is pointing, and on the left is the adder from the measurements on the actual model. And then you can see what kind of repeatability you can get in your sensor model, which should be a sub-pixel if you want a good georeferencing accuracy. Yeah, and then you have stability, right? Your camera needs to work outside a. Can you guys hear me or?
Yes.
Yeah, sorry. I was hanging here. So, okay. Yeah, it needs to work outside a controlled environment in the lab. So you need to take care when you're designing a system about the thermal variation, pressure variation, vibration, and EMC. So affected parameters by this environmental parameters can be sharpness, distortions, the radiometric accuracy can change. One thing I didn't mention in the radiometric calibration is that if you don't stabilize the FPA of your detector, for example, ambient temperature change will change the quantum efficiency of the detector, meaning that your radiometric calibration will be compromised. So if you want an accurate traceable calibration, you either need to compensate for this or you need a stabilized detector. And of course, spectrally, you can get shifts if you have thermal changes and pressure changes. And of course, the geometric characterization or stability can change as well. Okay, then now I went through the noise sources and the quality parameters in the actual camera. And then for any good or bad camera, whatever, you can always operate it in a way that introduces errors as well. Here, the example shown here is a flight done in Italy, 5 flight lines where there's 900-meter difference from the highest and lowest point, where we have sub-pixel co-registration accuracy everywhere because you're doing it correctly, the way you, the whole setup of your operational in an aircraft. Okay, so what can introduce error or noise in an airborne or UAV setup? The most important of all is that you have to time tag all your frames in your camera. I will go into a bit more detail in the next slides. In INS data for UV, for example, it's important that you align it quickly and you align it in the best way. The INS accuracies can play a very big impact on your georeferencing accuracies. And when you go into the co-registration of a veneer and sphere cubes together, you want to co-registrate and merge them into one cube, right? Then you have the DSM and DEM plays a big role. A role can be the stabilized platform plays a role. The sensor model, of course, you need very accurate sensor model as explained, and a very good pore set calibration. This is a normal hardware flowchart for an airborne or UV setup, where you have here a couple of cameras, the sphere and the veneer camera. You have a data acquisition unit that controls the cameras, and data is stored on this one. You have an event cable going to a navigation system, which time tags every frame, or maybe not every frame. I'll come back to that. And then you have a touchscreen here where you can control everything. On any navigation system, you have an event input. At least I haven't met anyone yet that doesn't have it. And typical timing accuracies on a navigation system is around 50 nanoseconds. Can for some go up to 100, 150, but it's very, very good timing accuracy. One limitation of the normal navigation system is the frequency of the triggers that it can be timed. So our cameras can go up to 1,000 hertz, so we cannot time every frame. So what we're doing in our custom PCB inside our cameras, we are the frequency generated, which is generating the trigger to the cameras, is divided down by a factor so that it's within the specification of the navigation system. For a drone system, it's divided down by a factor of 8 here, and then that frequency is timed on the navigation system, meaning that every 8th frame will have a very accurate GPS time tag. Then you have the INS accuracies, and here it's many different solutions are used. You can use systems from 1,000 euros to 200,000 euros, depending on what your needs are, right? For our UAV system, we use APX15, which is a good compromise between price and performance. So in a post-process mode here, you can see that you can get down to 2 centimeters accuracy. In the roll and pitch, you have 0.025 degrees accuracies, and our pixels in the 620 is 0.03. So it's a little bit better than 1 pixel. And in the heading, it's 0.08. So there is another quality parameter that you have to take into consideration when selecting a navigation system. So if you're flying an airborne system and you're flying long lines, if you have the mid-level systems, they tend to actually drift off quite fast in the heading. So for example, this APX system, you cannot fly longer than 5 minutes flight lengths, then your heading will drift off. So you need to know what kind of flights you're doing and then choose a navigation system. Yeah, and then usually, at least for drone operations, you use a gimbal. And then the limitation of your absolute accuracies will be maybe around, at least with the gimbal and everything we use, around 10 centimeters if you only use a single IMU. That's why we use usually a dual IMU. So we also put an IMU on the airframe to compensate in real time the dynamic level, right? Because the antenna is mounted on the IMU and it's always changing when your gimbal is moving. And then you go down to the 2 to 3 centimeters accuracy. Here is a normal processing flow chart for airborne and UV data. Yeah, it looks like a lot, but it's all done with a click of a button in a script if you want. So you have the air, right, running, storing the raw data, high-space RAD, taking all the calibration data, which is now stored in a binary header in the image file as metadata, so you don't need any files following your image files. They're all in the same file. And then that converts to sensor radius. This is shown for an Applanix navigation system. So then you use post-processing software to process it to an event file, which is basically the every 8th pulse time. And then you have the 200 Hertz INS data. And then in high-specs nav, you actually sample this data into the mid-exposure of every frame, which you need very accurately, right, to know the position of your camera. Then with that file, with the sensor model or the geometric characterization from our lab and an elevation model, you can do the auto-rectification. And if you want reflectance, you can use a software like Atcore to get reflectance and do the atmospheric correction. And then something about the elevation model and surface model. So typically, airborne use as ½ meter error or uncertainty in your height is not a big problem when you're flying 1,000 meter plus. But for UV systems, ½ meter error in your height can have a huge impact on the accuracy in the georeferencing, or at least the absolute accuracies, which will show in bad overlap between flight lines. I will just show an example here of a couple of images processed with flown at 80 meters height, where you have trees, high trees, where we have used photogrammetric solution to make a DSM and DEM. So the DEM, I didn't mention that, that's the digital elevation model. That's basically the elevation of the ground. Well, the DSM is the surface, right? So that the surface also have all the trees in the model. I hope it's big enough for you to see, but on the right side here, you can see you have the elevation model. So you can see that, of course, I should have been focusing in here, but there is on a pixel level here, no co-registration problems between the flight lines on the ground. But if you move up to the trees, you can see here that there are basically big co-registration problems because this tree suddenly stops, right? But if you go here, when you have the surface model, you will see that you have both good co-registration on ground and in the trees. There is many, depending on your system, can be reasons to choose a DM over a DSM because, you know, it can be steep trees. And if you don't have perfect control of all your data products and you don't have a co-registration on a pixel level, a DSM might correct things very wrongly, right? If you have mismatch. So we usually use DSM because we have a co-registration on the less than a pixel or better than a pixel. And another example here, and this is also a good example when you're flying a UAV, because you usually tend to plan the flights when you have an altitude on the ground. So then you have a plan usually at 25% overlap. But if you, and you see when you georeference 3 flight lines using the ground altitude, then you will have complete coverage. But you will have the error here in the overlapping regions or in those 2 places. Well, if you go to the DSM, you will have the perfect overlap. But as you can see, you don't have overlap actually for some areas due to the fact that the trees are high and the field of view are lower, and you're not covering that area actually. Yeah, then just as an example of this, how accurate you need a surface model to do georeferencing well. If you're flying 50 meters altitude, with our system, you have 1.3 centimeter pixels. If you have ½ meter error in that surface model, that is 8.8 centimeters error, which is 7 pixels. So you will have a 7 pixel co-registration error in the overlap between flight lines. And again, if you have INS data and you don't have base station, or your accuracy goes up towards 20 centimeters, you will again have very bad overlap. But bad overlap doesn't mean that your image looks bad. Your georeferenced image can still look good, and you can still merge sphere to veneer, but the absolute overlap or the absolute accuracy will not be good. That's why, of course, the combination of using high specs with LiDAR and or photogrammetry is a very good combination, because then you will always have a very accurate surface model acquired at the same time as the flight. Then for stabilizing mounts for airborne and UAV, I would probably 80% of our airborne customers doesn't use a stabilized mount. They hard mount the camera to the frame of the body of the aircraft or on a passive damper. For fixed wing aircraft, that's not a big issue because the movements are quite slow. So your navigation system have no problem picking them up and compensating for them afterwards. The only impact it will have is that you have to plan larger overlap between the flight lines, so you need more flight lines. While for octocopters, you definitely need a gimbal. The top graph here shows you the flight path from a demo flight we did in China. Same time of day, just half an hour in between these two flights. But you can see how the movement of the field of view is on ground, right? This will increase your blur on ground because it's moving a lot, because your UV always try to stay stable, right? While you can see when we add a gimbal to the system, it compensates for all this movement, and your footprint on ground will be a lot more similar from frame to frame, which is important. Then, to get the extremely good absolute accuracies, you need a bore sight calibration. And all our systems are bore sight calibrated at NEO or UV systems. So when you get it, you can do direct georeferencing from day one. And direct georeferencing is meaning that you can georeference your data without having ground control points on the ground. And to do direct georeferencing, I said, you need an accurate bore sight. And to do an accurate bore sight, or what an accurate bore sight is in a veneer sphere system, means that we find the roll, pitch, and heading offsets between the sphere coordinate system and the veneer coordinate systems. And then you find the roll, pitch, and heading offsets between the IMU coordinate system and the veneer sensor. With those offsets, you can co-registrate and merge your data into one cube and get perfect overlap if you have a very good DSM. Not perfect, but nearly. So an accurate bore sight calibration cannot be achieved, of course, if you don't have a very accurate sensor model from the lab, right? You usually need many ground control points to do a good bore sight. How many points depends on the accuracies of your INS or navigation system, and the accuracies of your DSM. But keep in mind, if you have an offset error, which is quite often on some DSM and DMs, this will result in the wrong bore sight. After offsets are found, it's straightforward to do direct georeferencing. And we use parts both for georeferencing and the bore sight. Here's just an example of the same demo we did in China, where we flew a couple of lines and did direct georeferencing. So the conclusion on the operational consideration is that high performance for remote sensing for airborne UV is that high performance time tagging for all frames are always needed to get good georeference data. To get good co-registration between veneer and sphere, that can be done with a high accuracy sensor model, high accuracy bore sight, and optomechanical stability. But you don't actually need a good DSM or a good INS data to achieve a good co-registration between veneer and sphere. But if you need good overlap between the flight lines, meaning good absolute accuracies, then you need a high accuracy DSM and a high accuracy INS data. And then the last slide on operational. So the most important parameter, which is easy to, might be easy to forget, is that after you have selected the correct frame rate or frame period relative to the altitude of flight and the speed of flight, you must, of course, optimize your integration time to get the best possible SNR in your images. This is super important. Then there is a group, IEEE P4001 group, which is working on a lot of the things I've been mentioning now. They are making a standard for characterizing hyperspectral cameras in the spectral range from 400 to 2500 nanometers. That's the range we make cameras. The standard will cover most of the detector and optical parameters in this presentation. The standard will present a way to visualize these quality parameters and a way to measure and characterize these parameters. NEO, HSpace, and other hyperspectral manufacturers are part of this group to define the standard. So we hope that everybody will start using this when it's finished. So I think it's very good that many of the biggest suppliers are part of it. Then a quick comparison between the good and the ugly. It's just a UAV example. Here you have, this is not the same UAV demo in China that I showed earlier, but it's another one where you see just a RGB image taken 3 bands here from our hyperspectral data, and where you see our spectrum, the very sharp 760 line here, and you can see the optical quality from the image. This is just I would say, I hope that you're not able to see big differences between hyperspectral cameras when you assess the quality in this way. But this is an example where this is very visible. This camera here is from a camera that on the datasheet has higher peak SNR than our camera. And they don't have a traceable calibration. So the data here is the final product from the customer. You can see here that you don't have this sharp 760 lines. You have a bluish haze over the whole image, which often is gray light, and you have some striping effects. And as I said, this camera on datasheet has a better signal to noise ratio than HSpace, or peak signal to noise ratio. But then if you look at, for example, the beginning of the spectral vector at 411 nanometers, this is the energy in that camera that you see. So it's a lot of noise and not many photons basically reaching the detector. And this is the same band for HSpace, where you can see persons, you're flying over persons there. You can see shadows, you can see that the image is still sharp. And at the end, just on the spectra, if you look here on the top, you can see the 760 line of the bad or the ugly. And you can see that it's actually the gravity of the 760 line is changing. So all these points here are from different places in the field. So meaning you have a quite large smile. So usually you should not see, as you see from HSpace here, you should not see difference in the spectral vector by selecting spectra, right? Different places in the field. Okay, so I want to sum up in one slide. It's impossible to say, I would say, something about the quality of the system from the top level specification, at least the way it's listed in data sheets today. Detector noise sources are typically not the largest sources of the errors in a hyperspectral system. Optical distortion, which cannot be read from the top level specification, are the largest contributor to reduce spectral fidelity in your data product. It's important for a manufacturer, at least we believe, to inform potential users or buyer of the camera, the performance in relation to all the above mentioned quality parameters. even if you have a good hyperspectral system, it's still possible to operate it in a way that's not optimal and will compromise the quality of your data. So you need to have control, and as a supplier, you need to train your customers so they operate it also correctly, because or else they can get bad data. And we hope, of course, that the IEEE standard will be a big step here in the right direction for showing the real performance of an imaging spectrometer. And of course, I am probably having similar presentation as this for 15 years now, and been focusing on the quality and characterizing. And we have been quite transparent for this last 15 years, and we have always delivered a 25-page test report with every camera showing the above specifications. That was it.
Excellent. Thank you, Trond. Yeah, myself, I'm actually looking forward to the standards committee putting forth their idea of standards, right? And, and everyone adhering to these so that we can really compare apples and apples across the board in some capacity. That's the whole point. But with that, let me open it up for questions. And in terms of questions, so it's not immediate chaos, we will, allow the individuals to either show their video or open up their mic and ask a question, and just be respectful for others if multiple people start talking simultaneously. So let's give that a shot.
Hi, Trond. I have a question here.
Yeah.
This is how are you? This is Pablo Royo from NRC. Thanks, Trond, again for excellent presentation. Do you foresee HSPECs to create cameras with less bands? The price point here is the issue, and you know that, and we know that, right?
Yeah.
And the new, multispectral cameras, they're mostly failing in these aspects of good characterization, good data. Do you see it from the technical point of view and for the market point of view, a potential compromise in number of bands, but lower price, so it's more applicable to the many fields hyperspectral can work?
Yeah, and my question is yes to that. We started off by introducing this industrial line called Balder in 2019, which is still quite a lot of bands, and still on the I would say probably not the range price range you are thinking about, Pablo. But we also have in 2019 started an application group, which is now quite large, which is working on applications helping our customers, right? And here the goal of this group is, of course, to help develop models for our customers, but also as input to R&D, right? If there is an application where it's a huge volume potential, but they need these 7 bands or these 12 bands, then we will definitely be open to designing that, as long as it's commercially, it's a commercial potential. Right?
All right. Thanks, Trond.
Open up for other questions. So clearly, you guys are you have been focusing on push broom scanning type systems, and that's your bread and butter there. Have you ever considered other technologies? Maybe, I'm sure you have, and deemed them inappropriate or not appropriate. And there's pros and cons to all this stuff, right? And so you try to maximize the given technology you actually have, and that's what you guys have been focusing on. There's other things out there too. What's your thought on that?
No, as I said, of course, we are always open to new technologies and considering them every year. We have, I would say, bi-monthly brainstorming meeting about all different technologies and what has happened. And so this is a continuous discussion internally, right? And the reason why we have always stuck to push broom is, of course, we can design sharp systems spectrally, spatially, with similar, the PSF being similar across the whole field of view and for all wavelength. And one of the key things is so we are coming from airborne, right? The first system we designed was from airborne, and it's that you're gathering all the spectral information at the same time, right? It's a key to us for reconstructing and getting the lowest spatial and spectral distortions in the data. So that's where we're coming from. And I'm not saying we will never do something else, but currently we are still sticking to that strategy.
Right, that works for you, right? And most of the, as we look across the field, that's, everybody's using some type of push from, that's the popular, and the P4001 standard, that's what is being looked at as well. It's in terms of a technology. I know that as well. Any other questions? I guess I'll have another one. I'll have another go at it. So I guess it's just going to be you and me, Trond. Uncertainties. Where are you? I don't think you reported. Maybe you won't report it. But where are you guys in terms of uncertainties with your CALs?
Yeah,
when
so
you say a radiometric CAL.
Yeah. So radiometric calibration, of course, it depends on your calibration of integrating sphere as well. But we use one with 2% radiometric calibration and 5% O2 in the visible range and 5% in the short wave range. And
okay.
Of course, here you can use. I think LabSphere can sell you probably 0.5% if you just pay enough. But that's the equipment we use today. And for the spectral calibration, we have 0.1 nanometers for the classical Vernier system and 0.2 for the shortwave infrared systems, which is a very small fraction of a band. So I'm familiar with the feel for that, for 2% Viz for radiometric CAL. Gotcha. Any other questions today?
Yeah,
I think Mark.
Oh, Mark has his hand up. I'll let him.
Okay, or you're done.
Yeah, go ahead, Mark.
Yeah, just a quick question. I don't know your technology, your cameras in detail, although I've seen them a little bit in the literature. And I'm interested in how, if your technology could be applied to two specific indoor uses. One would be machine vision, and the other would be cultural heritage imaging, that is the imaging of ancient documents, where you would perhaps want hyperspectral channels that are fewer than for remote sensing.
Yeah, and my question to us is to the cultural heritage is yes, we're working in that field for a long time, both from airborne perspective and for example, the museum in Louvre in Paris bought our system in 2009, our art scanner, which is scanning both art and ancient items in the basement of Louvre, right? And that's a common use of our technology, actually. So after that, we have sold a lot of scanners like this to that application. And I don't remember what was the first one, the first question?
The first was about machine vision.
Yeah. And in 2019, when we launched our industrial cameras, we also at the same time purchased a software company called Predictera, which is doing machine vision, machine learning, and using chemometric algorithms together with machine learning algorithms in this field using our cameras. So this is something the application group, which I briefly mentioned earlier, is working on every day on different applications.
Excellent, thanks.
Yeah.
John.
Okay, well, thanks a lot, John. This is an excellent talk, fantastic and very appropriate for the students that we have. I noticed on your summary slide, you said detector noise sources are typically not the largest sources of air. And I'm just wondering, from a radiometric noise perspective, would you say that that's true, or what are the largest sources of air?
So let's say you can, when you're looking at an integrating sphere, right, where all the energy in all the pixels, let's say you are looking at what is your signal to noise ratio in 1 pixel. Then if you have the same spectra in the illumination next to that pixel, both corresponding pixels, then your detector noise sources will be the limiting factor. But if you go, we are making imaging spectrometers, right? So we want a spectral fidelity in every pixel, no matter what is in the pixel next to your pixel of interest, right? I'm trying to get to the correct slide here. Let's see. Here we are. There. So this is based on a scene flown over forest, some urban, right, for airborne, where we added the spatial keystone spatial mystery expression, right? And so the spatial mystery expression is by far the largest contribution. Because this is here in average over all this data. It gives you, if you have 30%, we make cameras less than 10% of a pixel, but a lot of suppliers have 30, 50, all have also seen 70% keystone, right, in your data. And let's say you have 30, then you have a 70% average relative error in your spectra. And then that's by far a lot higher than the photon noise.
Great, thank you.
So there was a question in the, speaking of keystone, there was a question in the chat, and I will read it. You can probably see it as well, but does the keystone correction need to be done in post-processing, or is it included in the corrected format provided by HiSpectral?
A very good question, actually, because there are some alternatives to doing that. All our classical cameras have the optics correct for keystone and smile. So the data coming out from the camera directly has this corrected. But of course, there are some benefits to not doing it. If you are not spending or making advanced optics for doing that, you can get more light through the system, a more sensitive system. And if you do that, then what this article here is showing is that you should resample, because this is a resample, the oscillating here is a camera with a lot of keystone where it's been resampled. And here you then show that the errors in your resampled end product corresponds to about 12% hardware corrected camera, which we call it, right, when you correct it in the optics. Yeah. So meaning that if you have a system with a lot of keystone, you should always resample it, because then you will have a camera which is about 12% keystone camera. Of course, that only is true if you have characterized the keystone well and your keystone is stable, right, with the environmental impact you have from airborne or from ground use. So
temperature, etc.
Yeah.
Excellent. We have another question in the chat, and that is this one's from Dean Riley. Trond, you're looking at extending the wavelength range to 350 nanometer in your veneers. That's sort of part one. Also, are you guys interested, or are you expanding your product line into more midwave and long wave? Equals a lot of money there, but
we have gotten a lot of questions on that topic. And we have said no, because we have, at least so far, because we have enough in the range we are. We have actually made some cameras down to 350, but not midwave. So for midwave and long wave, we have a partnership with Telos, where we have been delivering contracts together. But so we don't have any plans to go to midwave or long wave.
Gotcha. So veneer sphere is where you are.
Veneer sphere is where we are, and we have enough to do. So.
Gotcha. Very good. Okay, I will just ask one last time for questions, and then we will wrap this this seminar, and our academic year for seminars. We'll wrap that up. Anything else? Okay, great. Trond, thank you very much, and I hope we'll be in touch. And actually, I will see you pretty soon at the Stratus meeting that is virtual. Anyone interested in that, please go to stratus-conference.com. I will type it in the chat, stratus-conference.com. And Trond will actually be giving a talk there. There we go. There's the URL. And so we look forward to that. And with that, I would like to say thank you, and we will end the session for today. Take care.
Great. Take care, guys. Goodbye.
Thank you. Bye.